Not even recording this. Let's start recording this. But like, what does it tell us about anything? Why or why not? So it doesn't tell us anything about a single observation, but like over the long span, right? And how large is large? I guess that's another question, right? And that's a bit of an open-ended question, if I'm being honest. Like, how large of a number do we need for it to be large numbers? It depends on how much accuracy you really want. This is probably the best way to describe it, right? The more trials we get, ideally, the larger or the more it should be closer to our theoretical probability, right? The more and more we conduct this, if we're truly using like a fair coin, that heads probability should be 50%, right? It should be getting closer and closer as we conduct more, right? If we roll a die, was it like 0.167 or 16 is the probability of one side? If we roll the dice like twice, right, and we're betting on the probability of a 4, it's already at 50% or something like that. But each trial we do makes it jump a little bit more and more towards that not expected value, the theoretical probability. Okay. Yeah, these first two questions are pretty much, I feel like that was pretty much, if you watch the notes, you should understand them. So what is an expected value and how is it computed? Should we always expect to get the expected value? Why or why not?
Is it 2 events and probability?
For what? The expected value?
Yes.
Well, the expected value, I believe, is just the actual value of doing it over again. Isn't it like doing it again as far as the whatever okay, so whatever from what this is what I get out of this is that to get the value that you are expecting or computing, something has to be repeated. And so it seems like, you have to repeat a certain amount of times to get the expected value, and then you vary from there. So I'm still kind of confused with this, but I'm just going to go with the flow here.
So I think you're correct.
Hopefully the professor will explain.
So I think you're correct in saying you have to do this a lot of times to get the expected value, right? Because we have to do the law of large numbers in order for this expected value to come true, right? We have to get large numbers or large number of trials to get this close to our expected value. And I think Anthony was saying something like how you do the value of the event times the probability of the event. I think that's what Anthony was getting at. These are all true, but what this is telling you is the average per game, right? And I should say win or loss.
So it's calculated by each of the possible outcomes.
Yeah, so we look at
each outcome will occur, and then like summing them all up will equal the value.
Yes, and so we're looking on average, if we play a game, how much will we win or lose, right? And so we take the value and we multiply it by the probability, and we'll probably have a few of it. Value 1, probability 1. Right? And then we have like the value 2, probability 2. So there's some value, there's some probability that we will get that value, right? There's some value here, there's some probability we'll get that value. The value can be positive or negative depending whether we're getting it or paying it, right? But that is the average amount you should expect per game. How is it computed? Value by, I think that's the words they use in the book, right? Value and probability. It's in your notes.
Yes.
Should we always expect to get the expected value? So, I don't know, let's say my expected value is 65 cents. I computed this thing and I expect to get 65 cents per turn that I take on this game. If I go and play that, should I expect to get 65 cents on the first game I play?
No.
No. Why not? Because this is what?
No.
This is on average, right? And so on average, you're not, I mean, you will make 65 cents on average, but each an individual turn, you're not going to make 65 cents, right? You might win
No.
$1 here. You might lose 70 cents here, right? Something like that.
Yes.
But all in all, when you sum it up and figure out what you're winning and losing over the long term, right? Using this law of large numbers, it should be close to like 0.65. So we expect to get this on average, but we don't expect to get it like every time, right? Kind of like how you can get a 70 average in a class, but doesn't necessarily making exactly a 70 on all your tests, right?
Yeah.
Something like that.
It's kind of like an assumption,
Like a what?
like an assumption or something.
Well, you're averaging it out, right?
Yeah.
So if you made like a 65 and then you made an 85, right? Or 75, sorry.
Okay. Yeah.
You'd make a 70 overall as your grade on your test, but
Mhm.
you never made a 70 on your test, right?
Yeah.
On one of them, you made a 65, on one of them, you made a 75. But when we average it, you would
It'd be
still get
70.
an average of 70 on your test, right?
Yeah. Okay.
But you're not going to make ever exactly, usually you're not going to make exactly the average, right? It'll be a little bit above, a little bit below. Sometimes you're given, sometimes you're taken on these problems. So sometimes you win some, sometimes you lose some, and then when you average it all out, you're winning 65 cents. So this goes back to like the casinos, right? The casinos can pay out $1,000 to one person, and that one person can walk out of the casino. He could be a winner, right?
Yep.
But guess what? There's like at least 12 other people around him, all throwing in their $1,000 and walking out of there broke and not wanting to talk about it, right?
Right.
Yeah. So a lot of times we only like to talk about when we win things. So there's some personal biases that come into play. Oh man. Yeah, I teach this, and then like it's like I don't personally have like any problems with gambling, but like I know like it is an addiction, right? And some people really do have problems with gambling. There is like certain things if you go in, I mean, I've been in a casino, I know this, like I've experienced it kind of personally. Like all those flashing lights, right? They get things pumping in your brain. And it's just like, oh, this is fun. Let's do this, It really it is really really hard to like kind of control your impulses, right? Sometimes when things are whizzing by around you, they know what they're doing really well, is what I'm trying to say. So beware. Like,
I think a lot of people get caught up into that is because of the euphoria of winning.
exactly.
It's not so much the amount of losing. I figure they know they're gonna lose, but it's the euphoria of winning.
It's that oxytocin rush they're getting.
Yeah.
Yep. Yeah, and they know what they're doing in the casinos. I'm just telling you that. They ain't there to lose money. Let me tell you. So decide whether each of the following statements makes sense or is clearly true or does not. It is clearly false. Explain your reasoning. So the expected value of me winning, of the expected value to me or of you winning of each raffle ticket you purchased is a negative 85 cents. Does that make sense?
True.
You're saying it's true? Why would you say it's true? Like, why would that make sense?
Because you can spend 85 cents on a raffle ticket and lose, and now you're 85 cents in the hole because you took that gamble to spend that 85 cents.
Yeah, I wouldn't. This doesn't necessarily say you're spending 85 cents. You could be like spending $1, and then like the rewards would total to like 15 cents benefits when we did the expected value, right?
I thought that was a negative sign on.
Oh, it
Yeah.
is negative, right? But this would be paying $1 for the ticket and maybe 10%. Maybe there's like
I don't think, can anybody else hear you, Professor?
Can y'all hear me?
No, he's
There we
cutting
go.
out.
Okay.
Am I cutting in and out?
mic.
Okay. Yeah, I would say like,
Are you bending over, Professor, or how is this working? Because as soon as you get to writing, it seems like you go out. I don't know how that is.
I'm like leaning in a little bit, but it shouldn't be like
Okay, so
cutting out.
I guess when you
I
lean in,
should be
it's
cutting
kinda-
in, if anything. I'm getting
Yeah,
wide.
you like go all the way out. As
Okay.
I'm trying to listen, and then it just like goes out when you bend over. So I kind of
Yeah, it's like we can't hear you at all.
yeah.
Okay, can y'all still hear me now?
Yes.
Yeah, I can hear
Okay.
you now.
Yes.
So can you repeat that what you were doing just a minute ago?
All right, so if I'm thinking about the expected value, this wouldn't be the amount I paid for the game. I know that might be a little confusing. And so I set up maybe like, I think this sums out to -85 or -85 cents. I could be doing it wrong. But there's like a 1 in 10 chance of you winning 30 cents and 1 in 10 chance of you winning 50 cents. But all in all, if this was a raffle, right? Would we expect the expected value to be positive or negative?
Negative.
It would definitely be negative because they would be making money, you would be losing money. That's the entire point of having a raffle, right? Is to raise money.
To raise money, yeah.
So if you're not losing money, that means they would be losing money, which is not the way a raffle works. And so I think Anthony was the guy that said it makes sense. It absolutely makes sense. I would just be careful. This isn't the amount you're paying for the ticket, right? This is the expected value of the game.
I see.
Yeah. There's a little bit of a distinction there, but I think you're on the right track with how you're thinking about it. If you toss a coin 4 times, it's much more likely to land in the order of heads, tails, and heads, 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 heads. Is that true? Hey, do we need all this noise? No.
It's false.
Why would you say that's false? Like, how likely is it to land on this, and how likely is it to land on that?
I mean, it's equally likely because they're independent events.
It is
So
equally likely. It doesn't matter how we do this. The chance of getting 2 heads is not the same chance as getting 4 heads, right? That is a different question. What they're asking is in this order, right? Heads, 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 heads. The order here is very important, right? Each trial is going to be what, a half? So we did the multiplication principle last time. If we wanted the total population of like all options of 4 coins, it'd be 2 times 2 times 2 times 2 times 2, which is what, 16, I believe. 4 by 4. So I believe both of these are going to have a probability of occurring 1 out of 16. If we wanted to list all the heads, tails combinations out there, each of these would be 1 out of the 16 possibilities we would get. So there are other ways to get what? 2 heads and 2 tails? Is what I'm also kind of trying to say. Tails, heads, tails, heads. Each of these events, and or if we're talking about order being important, right? Each of these events is all like 1/16 likely. I can write out all the 16 different possibilities. All of them have 1 in 16 chance of getting chosen randomly, right? So they're talking about outcomes, right? There's outcomes, and then there's that thing called events. The event of getting 2 heads would definitely be a lot more likely than the event of getting 4 heads. But if we're just talking about outcomes, it's equally likely that you're going to get this outcome as you're going to get this outcome. Every outcome is equally likely. Questions about that? Are we getting that? Okay, understanding the law of large numbers, suppose you have a fair coin 10,000 times. You're going to flip it 10,000 times. Should you expect to get exactly 5,000 heads? Why or why not? What does the law of large numbers tell you about the results you are likely to get?
I don't think that you should expect it, but the probability of flipping it for 5,000 heads out of 10,000 flips increases with each flip because of the law.
Yeah, it should get closer to this, right? Is that what you're saying?
Yes.
Yeah, it should get really close to this. It might be a little bit above, it might be a little bit below, but like if we do 100 flips, it's probably going to be further away from 1/2, right? Ideally, we want things to be 1/2, or the probability to be 1/2 is the theoretical probability. In reality, reality is messy, so the frequent, was it the frequency, just, no, that's not what it's called. I can't think of the word now. Relative frequency, that's the word I'm looking for. The relative frequency should be really close, but it's not going to be exact, right? Reality's messy. But the more we do, the closer we should get. What does the law of large numbers tell you about the results you're likely to get? It should be close, but it's not going to be exact, right? What do they say? Okay. Whew. Find the expected value to the company per policy sold. If the company sells 10,000 policies, what is the expected profit or loss? All right, so I think we might have to do some number crunching now, starting. We're finding the expected value to the company. So if they sell a policy for 300, am I getting this 300 if I work for the insurance company? That's what they're asking. They're saying, I work for the insurance company. If the company sells 10,000 policies, am I getting this 300 or am I paying the 300?
The insurance company is getting it.
It's getting it. And again, what I'm going to do is I'm going to do value by probability. So I'm going to get this 300. So this is going to net positive in my pocket, right?
Right.
And what is the probability I will get this 300 if someone buys this insurance policy? It might seem silly, but what should I multiply this by? What is the probability I will get this?
1.
It is 1. I am guaranteed to get this thing. Okay, so we got 300. Based on past data, 1 in 100 policy holders will file $10,000 claim. I want to create some sort of sum. Am I going to pay out $10,000 or am I getting the $10,000?
You're getting the
Paying out.
10,000 if you file the claim.
I'm working for insurance.
Oh,
Am I paying
Oh,
that
I
or
don't
am I
know.
getting it?
Dang.
Insurance is paying that out. So I have to pay out 10,000. And what's the probability I will have to pay out 10,000?
1 over 100.
1 over 100.
All right, so I'm creating this sum. What else do I have? I could pay out 10,000. I could pay out, what is it, 25? So is this positive or negative?
Negative.
Negative 25,000. And what do I multiply it by? 1 in
250.
250. And then the last thing I think I have is what, a $50,000 claim? 1 in 500. So it's the value of the event times the probability of the event. This is my expected value. And so 300 times 1 is going to be 300. Multiply these two things. I would probably, if you're doing PEMDAS, you want to multiply these things before you add and subtract them. So this should be 300. This should give me a negative 100. 25,000 divided by what, 250? Should give me 100 again. And 50, 1, 2, 3, divided by 500 should give me, oh, this is poor copy. I think the way insurance works. What's my expected value of this thing? Did I do that right? Well, I guess so. This is the way, I just shouldn't say it. This is the way insurance probably should work, but it's not the way insurance does work.
0?
So,
It is zero.
so Professor, did you go 300
Times 1
times 1?
gives me what, 300?
Yeah.
I'm doing 10,000 divided by 100 is going to give me 100. 25,000 divided by 250 is going to give me 100 or negative 100. 50,000 divided by 500 should give me 100.
Oh,
500, 25,000 divided by 250.
Which one divided?
Is that 2,500 divided by 250?
Yep.
And it's 10.
well, so the next part of the question is if the company sells 10,000 policies, what is the expected profit or loss? Since our answer is 0.
Yeah.
Yeah.
Go ahead and say it.
The answer is 0. That's
It's
crazy.
0. If they're gonna make $0
What
per
is
policy,
that?
they're gonna make $0 in 10,000 policies.
Oh my
I don't like this problem too
God.
much because it's not very
So-
realistic. Insurance companies are not there to lose money. They are definitely making.
Yeah.
They are betting on the odds of you dying. Basically, is what they're doing. That is really what they do. I mean,
Oh my
it should be a positive number. I don't know why they gave this. Is silly. Yeah, insurance monies are definitely making money off of it. It should definitely be a positive number, and they should be making money. They got employees to pay, bills to pay.
I wonder what the answer they have in the book is because
It's
that's
0.
just really,
Yeah, I'm checking it. Yeah, it's 0.
that's so dumb.
Yeah, it don't make no
Well,
sense.
that's so silly.
Yeah, it's silly. They did it. Yeah.
6.
No, it's kind of dumb. They should have gave you something positive and made you go what 10,000.
Yeah, yeah.
So let's assume we didn't do that and it wasn't 0. It is 0, but if the company sells 10,000 policies, what is its expected profit or loss? Let's say we got $5 expected. I'm going to make $5 per policy that they sell. How would you figure out if they're going to sell what 10,000? Policies. IES, is that policies? IES, that looked weird. That looked too much like policies. If we're going to make $5 is our expected value and we're selling 10,000 policies, how much money would they make?
50,000.
Just so we get this. Expected value is expected value per policy, right? So we'll be making 50,000 on just so we have some numbers that aren't 0. Because insurance is definitely there to make money. Maybe I'm interjecting myself, but I feel like there's some things you probably shouldn't make money on. People's lives is probably one of them. We know people need water. We provide water for everyone. It's not like people aren't going to need insurance, right? It's like it is a necessity to some degree to have insurance. It covers your butt when things do happen, right? So I'm not trying to say insurance is like necessarily evil in of itself, but like I don't think the way that we handle it is maybe the most productive for our society. Maybe that's the way to put it. It's literally a game where they'd be gambling on it and gambling on the odds of you dying, right? It's not much different than like a gambling game. Or at least the way we figure it out. So 23 is the gambler's fallacy. Did I jump? Is this in this section? Yeah, this is in this section. The next section's over risk. That's right. Suppose you play a coin toss game in which you win $1 if a head appears and $1 if a tails appears. And the first 100 coin toss, heads comes up 46 times and tails comes up 54 times. What's the percentage that heads has come up in the 100 tosses? What is your net gain or loss at this point? So we're getting what, heads 46 out of the 100 times. What is the percentage there?
46.
Yeah, don't break your brain too hard on that one. 46%. What is your net gain or loss at this point? How are we figuring that out?
Do you
I mean,
add them
wouldn't it-
together or do you add the percentages together or you?
So you're going to get $1 if a head appears. They're going to get $1 if a tails appears.
I mean, wouldn't it just be $4 loss?
It would be, oh, I think you'll be careful. Because I think you got $46 and they have 54. So it's insane.
Would it be $8?
Yeah, I think you have to subtract the two to get them, right?
Okay.
You had to pay out 54 and you gained 46 is another way to look at it, right? This is our gain. This is our loss. They got paid every time they got a tail, so you had to pay that. So it should be 8. I hope that's what they're doing. Yep, okay. Suppose you toss a coin 200 more times, a total of 300 tosses. And at that point, heads only comes up 47% of the time. Is this increase in the percentage of heads consistent with the law of large numbers? Explain, and then they want to know what is your net gain or loss at this point. So we have 46, and it's like 46% at 100 flips. And then they say, now we're doing 300. It went up to 47. Does that follow the large of law numbers?
Yes.
This is exactly the law of large numbers. We go from 100 to 300. It is getting closer to what number? 50% is what the law of large numbers tells us should happen. So it is definitely following the law of large numbers. Are we making more money? So if we have 47%, how many times did we get heads? How many times did we get tails?
Seems like we're just breaking even.
141 heads, 159 tails.
141, 159. And that was by doing 47% of 300 flips, right? And then the other thing was that 100 minus 47 is what, 53? 53% of 300? So I won $141 and I had to pay out $159. So how much money am I netting here?
Negative 18.
What I'm netting here, my net is so we're gonna keep playing this game. If this is happening, would you want to keep playing the game?
Probably shouldn't.
No.
Probably shouldn't. Like we're losing more and more, right? It is going up and it is getting closer to being fair, right? But it doesn't seem like it's working out in our favor so far. How many heads would you need in the next 100 tosses in order to break even after 400 tosses? Is this likely to occur? So now they're telling us the number of trials is we're going to do 400 trials total. So to break even, how many heads would we need? That's probably the first question to think about. Might make it easier. How many heads, how many tails are we going to have if it's going to be break even?
What, the same?
Yeah, so the same. And if we're talking about 400, that would be what? How many?
Just 200 each.
Yeah, 200 each. This is what we need. So how many more heads would we need to get here? Was what they're asking. We started here. We want to get here.
59.
Yeah, exactly. We're on 41. We want to know the difference of these two things. Is it likely? And remember, we're going up. This is going from 300 to 400, right? From this previous problem. We're going to flip it 100 flips. Is it likely we'll get 59 flips and 100 flips?
Yes.
Yeah, it probably might happen. It's a little bit high, maybe, but it's pretty close to 50, right? We're expecting about 50 of these flips. It's still a small number. 100 flips isn't really too big. I would say it's probably likely to happen. It's not completely unheard of. They said it's possible, but not likely in the book. So I guess that gives you an insight into what the book is thinking, what I'm thinking. I would say it's not completely unheard of, but I guess it is a little bit high on the 50 end, right? It's almost 60. And then part D, what does part D say? Suppose it's still behind. Suppose that's still behind after 400 tosses. You decide to keep playing because you are due for a winning streak. Explain how this belief would illustrate the gambler's fallacy. So I have 400 tosses, and I get to toss 401, right? I'm on toss 401. What's the probability I get this out on the individual flip itself? What is that probability?
1 and 2.
It's still half and half, right? So each flip, the probability is still going to be half and half, theoretically, right? In reality, when we flip it, it's either going to be a heads or a tails. It's going to be one or the other. So relative frequency wise on a single flip, it's not going to be a half. It's either going to be 1 or 0. It either happens or doesn't. When we get 2 flips, we can actually get a half, right? Or get more flips. Okay. And so how does that illustrate gambler's fallacy? And what is the gambler's fallacy? Like what does it mean? I think the key word is probably the winning streak, right? So is it possible to flip a coin and get nothing but like heads for 5 or get tails for like 5 flips?
Yeah.
Yeah. That's completely possible. Am I due a heads on the next flip?
No.
No. So overall, in the long run of things should average out to 50%, right? But in the short term, can we say anything about runs and things of that nature? No, and that's the gambler's fallacy. We start doing this thing and we go on this little streak of winning and we say, oh no, I might lose pretty soon. Not necessarily. Or you might lose and you might say, hey, I'm due a win pretty soon. Not necessarily. There are things such as streaks, right? It doesn't say anything about the short term is what they're trying to get at with the law of large numbers, right? And people make this misinterpretation where they say, well, I have a streak, it has to go the other way. It absolutely does not. Not in the short term. We do not get that kind of guarantee in the short term. Law of large numbers is a long-term sort of thing. Just like how you can walk in a casino and leave with a bunch of money, right? These streaks absolutely do happen. But when we average things out and take things over long periods, we start getting the law of large numbers, right? It starts behaving more like our ideal probabilities that we're figuring out. Or theoretical probabilities, I guess is what they call them. So we got this guy, lottery draw. Consider a lottery game in which 6 balls are drawn randomly from a set of balls numbered 1 through 42. 1 week, the winning combination consists of balls numbered 5, 12, 23, 32, 36, 41. The next week, they got these 6 numbers. Is the second winning set more or less likely than or just as likely as the first? So this, which one is more likely? Which one's less likely? Are they equally likely? What is the deal?
I mean, they're both equally likely.
What about this? It says like 1, 2, 3, 4, 5, 6. So I think the thing with this is like people look at this and they're like, these numbers look completely random. These numbers look like they're in some sort of order, right?
To me, it's less likely because the number sequence will not happen on the second row. I mean, if that's what he's saying, if you think it's going to happen the next week, the same thing, no. That means you would be able to analyze the lottery and be able to win a lottery no matter what.
So this is the way I would think about it. These are like the and probabilities that we were doing in the previous section, right? What is the probability I will get a 5 out of this thing? If we have 42 numbers, it's going to be what? 1 out of 42 for this thing? This one, I think
42.
I think it drops down a number each time, like 1 out of 42, 1 out of 41 now, 1 out of 40, 1 out of 39, right? 1 out of 38, 1 out of 38.
That's if you're taking the numbers, right?
That's if we take the numbers, we take them out, right? It's
if you take the numbers out, but I don't think he's taking them out.
Yeah, but if you look at it like, okay, so 1, 2, 3, 4, 5, and 6, yeah, those are incredible odds. But then you look at it like, oh, 5, 12, 23, 32, 36, and 41 are my lucky numbers. What are the odds that those will all be drawn? It's kind of like the same thing. Like it's still.
Yeah,
you most likely won't get those same numbers again. I don't know. It's like I've never seen it's been like maybe like you said, like the probability of the continuing over. You might see the numbers like 3 years from now or 4 years from now. You might.
Okay,
Sorry, go ahead, Professor.
So we're taking these balls out, right? If I draw a 5, there's a 1 in 42 chance I will draw that 5. After I take the 5 out. Doesn't matter what number this is. It doesn't really matter what number this is, right? Every number is going to be equally likely, is what they're trying to get at here. Whether I do 1, 2, 3, it just looks like it shouldn't be equally as likely because this fits a pattern and that one doesn't, right? But it's still going to be the same odds. If I want to draw one ball, it's going to be 1 out of 42. It's going to be 1 out of 41. So this is as likely if they're all drawn at random. They are going to have those same odds. So I didn't even calculate this, but this is kind of from that previous section, the and probabilities, right? We're going to multiply these things together. I'm not even going to calculate the number, to be honest. But if I wanted to calculate the probability, I'd be calculating the probability the exact same way. These numbers are drawn at random. Just because they happen to fit a pattern doesn't really mean anything here, right? So it might seem like they're less, like this would be less likely because it fits a pattern or something weird like that. But things that fit patterns are equally as likely as things that don't. If we're doing everything at random, I think they're drawing it without replacing it because you can't get double numbers, I don't think. Yeah. Okay.
Do we multiply the 42 times the 41 times 40 times 39 times 38 times 37?
Yeah,
Is that how that's working?
It'd be one out of however many that is. I didn't even calculate.
Okay, all right, no problem. I just want to
And
know what we're
these
doing.
odds, the main point here is that they would be the same odds, right? Of getting this string of numbers as getting this string of numbers. All the string of numbers are going to be equally as likely. It doesn't matter what the numbers are. Every ball is equally likely to be drawn, right? It says it somewhere in there. So if every ball is equally likely to get drawn, it really doesn't matter what the number is so much.
Mm.
Were you saying like getting the same number? Is that what you're talking about here?
So I don't know. That's a weird question altogether, and an explanation of it. It's like, okay, so you want, the same number is saying that they're drawn randomly from a set of balls.
Mhm.
1 week, the combination of balls numbers that number, 5, 12, 23, whatever. The next week, the winning balls are 1, 2, 3, 4, 5, 6. Is the second winning set, which is the 1, 2, 3, 4, 5, 6, more or less likely than, or just as likely as the first? In other words, they're going to say, asking you, is that number going to repeat itself? That's what I'm thinking. So I don't know. I'm just confused. I'm just learning it here. But that's what I think they're saying.
I don't think they're asking about like, is this likely to repeat itself? I think they're just asking, is one of these more likely than the other? And they are both equally likely to happen is what this problem is trying to get at.
Oh, okay.
If we're drawing 5 numbers at random, it's going to be the same thing as drawing 5 numbers at random. It doesn't really matter what those numbers are. Now, in reality, right, like this is the ideal probability, the theoretical probability. In reality, when we do relative frequencies, you might find certain patterns in lottery numbers that aren't there. I think that's been done before, and people have kind of cheated at the lottery doing that. So sometimes things aren't completely unbiased when people try to make them unbiased, right? Okay, so house edge in blackjack. In a large casino, the house wins on its blackjack tables with a probability of 50.7%. So you might notice that's not a lot, much larger than 50, right? They just have a little bit of an edge there, like 50.7. All bets at blackjack are 1-to-1. If you win, you gain the amount you bet. If you lose the amount you bet. If you bet $1 on each hand, what is the expected value to you on a single game? And what is the house edge?
Do we need to know how many hands are in a game of blackjack?
I don't think you need to know how many hands are in a game.
Okay.
Or there's one hand in one game is what it is. There's $1 on a hand. One hand
Oh,
is
I
a single
see.
game. Yeah, they're
Okay.
using it interchangeably. So if I bet $1, if you win, you gain the amount you bet. If you lose the amount you bet. So if I win, I bet $1 and I win, how much money am I getting? That might be a weird way to ask it. Because there are a few ways you could probably figure this out. I guess we could keep it consistent. If I'm going to pay $1, You could do this, right? I'm guaranteed to pay $1. And if I lose, what do I get?
You lose $1.
If you play 100 games, you get $100. But if you lose, okay, so if you, okay, so if you win, if you pay $1 and you play 100 games,
Yeah, there are a few ways. So I'm like trying to think about maybe the best way to set this up. Because one way is we're paying $1, and if we lose, we're not going to get our dollar back. We're going to end up just like forsaking this $1. But if I win,
so
I
you
will
gain
win
$1.
what? I will win $1. And if I win $1, what's the probability I will win $1?
49.3%.
49 point, yeah, 3, yeah, on minus 50.7, yeah. Oh, percent, dang it.
Sorry.
Over here is what I should have done, sorry.
It's
No, that was
0.49.
me.
Do you round it off? Or is it 0.493? Do you round it off?
So 0.493. We're going to do -1 plus 0.493. And I think what I'm getting is a negative 0.507. Or you're going to be losing around 50, what 1 cents per game? See. Seem right. I'll say just 0.4. No, it's not correct. I think we have to do it. You're going to pay $1, and if you win, you're going to win $1 back. I think we have to do, we're going to win $2 back. Does that seem right?
No, if you bet $1, you just win $1. Because you don't pay, in other words, you're not betting for another $1. You just paid that $1.
I think you get your $1 back and you get.
No. That's it,
Well,
your
no,
dollar
actually,
back.
if
You
you
just
look
get
at
your
it,
dollar
if you-
back. That's it.
Yes. No, you're going to get $2 back because you're going to get the $1 you bet, and then you will get an additional $1. So I think that's where I messed up here.
Okay.
This is coming from the bet fact that you bet $1, so you have to get the $1 that you bet back. That's what I did. That didn't make sum up. I told you there's multiple ways to do this, so let's retry it. So one way you can look at it is that you're going to pay $1 regardless of the situation. If you win, you're going to win $1, which means the total amount, the total value of that, the amount that they're going to give you is actually $2. And we have a 0.493% chance of getting that. And so if we do a -1 and we add 2 times 0.493, that gives me 0.986. Which, what does this mean? I guess if we round it, it would be losing a little bit over a cent each turn. So you're not losing much more than over a cent. think the book just says -0.043. Yeah. They do the 0.4 of a cent on the book. So I think you can do it without looking at the fact that you are paying $1. There is another way to do this. And so this way might make more sense to you. I believe if we pay, we're going to lose $1, 5, I can't even, 507. I believe if we do this, it should give us the same amount. If I put my decimal in the right spot. Does that give us the same amount, 0.493? Yes, I think that will give us the same amount. So there is a 50% chance you're going to lose $1. There is a 0.493% chance to win $1. Is another way of looking at this, right? And I think this is what was happening in my brain. I was crossing this approach with the other approach. I knew there's like 2 different ways to get it. So what I would do is I would look at both of these. I would see which approach you like better. To me, this one looks a little bit more clean and direct, I think. I'm going to lose $1 50% of the time. I'm going to gain $1 like 49% of the time. The other way is to account for the fact that you've already paid $1. And if you've already paid $1, well, if you lose, you just don't get anything. I could have said 0, right? I could have added 0 and a 50. I could have added a 0 in there, right? It's not going to do anything to it. If I've already paid my $1 and I lose, I don't lose anything, and there's a 50% chance of that happening. If I win, I'm going to win the $1 I paid, and plus I'm going to win a bonus $1 for winning, right? My winnings itself. And it's going to be 0.493. This is easier for the insurance one, I believe, if we set it up this way. Like this makes way more sense for the insurance problems when you set it up this way. I feel like this way probably makes a little more sense with this problem. It's a little easier to solve maybe this way. So there are basically 2 ways to solve these probability problems. One is to account for the fact that you've already spent the money, and the other is to not account for the fact that you spent the money, right? Okay. Sometimes it takes me a minute to look at these. We're in blackjack. Bet $1 on each hand was the expected value to win a single game. Is this a good game to play? Like, what is an even game or a fair game? What is that referred to as? What would the expected value of a fair game be? Have we talked about that? I mean, maybe I didn't mention that.
Like a 50-50?
Okay, so 50-50. But what
So
would be the probabilities? Yeah, the expected value would be 0, right? If this was a 50% chance of winning $1 and a 50% chance of losing $1, it would average out to 0. So a 0 game is what we would consider like a fair game. Everyone has an equal opportunity to win it, all the players involved, right? If this is a negative amount, what does that mean? The casino is making money, you're losing money, right? So again, they don't really have to have very good probabilities or odds. They just have to play enough games, right? They're going to win this amount per game that they play. And we're about to see that. If we play 100 games of blackjack and we bet $1 on each hand, how much you expect to win or lose? Well, hopefully you don't go into a casino expecting to win money. It's not a good strategy. But if we're losing this much per turn, part B is I do what with this? I multiply it by
100.
by 100.
I multiply this by 100, put it over 2. I believe I should
$1.40. Okay.
NC says if you play 100 games blackjack in the evening and you bet $5.
How much should you expect to win or lose? So betting $5, I think the easiest way to think about it is that you're doing 5 $1 bets, right? So if this is what a dollar bet's going to get me, how much will 5
No,
of
it's
them
a
get?
$5 on each hand.
Mm-hmm.
Are you
So
doing
this-
C?
So times it by 5.
Exactly, right? If
Yeah.
1.4 by 5. So I think I'm going to lose $7 or a -7. So either write the negative sign in there to represent it's a loss, or you got to say lose, right? Some way or another, represent it's a loss. And then D, was there a D? Here we go. If patrons bet, do the little pinky thing, $1 million on blackjack in one evening, how much should the casino expect to earn? Explain. Again, this is the per game amount. So if we're going to do $1 million, what is that? 6 zeros we got to move that thing? Moving it 3, move it what, 3 more? I think that's going to give me what? I think we're losing 14,000 now. Does that seem like $1 million times 0.014?
But it's how much should the casino
How much would the casino make?
expect to earn?
Oh, well, if you're going to lose
Yeah.
14, guess what? They're going to be the ones making that money. That's the other end of it. Sorry. Shouldn't be negative then. Should be positive.
1 million times what?
1 million times this thing, the 0.014.
Oh, okay. Got
This
it.
is the per game, right? For each $1 you bet in the game, per game, that's how much you're going to lose. So if you bet $1 million,
Times
you're
this
going to lose $1
million.
million times that, or you're going to lose 14,000, or the casino is going to gain 14,000. So again, I
But
said
wouldn't it be more than that? Because if they're betting $1 million and there's a 50.7 chance of the casino winning, wouldn't it be like a little over $500,000 that they're earning?
They would get that, but you would, it's like they would get you would expect them to get, what is it, 50.07, something like that?
No, it's, well, I'm getting four.
But you would be winning like 49 or something, right? 49,300 or something.
Yeah, but it's for $1 million.
You would have to take these two amounts from each other, I think is what you're doing. Did I do 1,000? Should have done 1 million? Another 0 in here?
Yeah.
So we would have to subtract these two values from each other, I think is what we're doing.
Okay.
Like you would make some money. They would absolutely be making that money, but you would also be making some money. So the difference between these two would be the 14,000.
Okay, so I
Okay.
took the 1 million times the 0.014, and I got 14,000.
Yep, that's it. That's how much the casino is making. Just like
So how much am I losing?
just like this, if I wanted to do it on this step, this might be a good step to do it on. Instead of 1, I'm going to go minus what, $1 million. In here, I'll do the million. This should give me the 14,000 if I converted my dollar to $1 million instead. It'll be negative because we're doing it from the player's perspective here, right? But it should be where they're getting the 14 from. Is that making a little more sense, hopefully?
So I'm doing it on my
Yeah.
calculator and it's equaling up to 10,400, negative 10,400.
Hmm?
Like if you went down and you subtracted them.
Are you doing the negative 3,456 by 0.507? Did I do it? Maybe I got my. No, it should be 14, right?
No, it's 14,000.
Yeah, it should be 14.
And she's not doing. She's
Maybe you got your
she's not
decimals.
multiplying. She's using that number, and she's not multiplying it. I think she's dividing it.
No, it's not that. It's whenever you go down, like if you move your paper up.
Where? What? Here?
No, like below the C.
On D is 14,000, right? We're doing what? 1 million times
Yeah, and casino bets a
0.014.
million on a million blackjack and
Is
one.
that what you're doing? 1 million times 0.014?
No, it was the 490, 300, and then the 500,000. I subtracted those two and it equaled.
Yeah, I reversed the order of these things. These things aren't right. It should be 493,000. Sorry. I threw in an extra zero in the wrong place is what I did.
Okay.
50.
That's what I was confused about.
Sorry, yeah. I threw in the zero in the wrong place. I tried to add an extra zero in there. I shouldn't have. And I ended up reversing the order of these things. Should be 493 and 50.7. Right. Sorry about that. All right, so that was what, 31 blackjack. We got one more in this section. We got to find the expected value of Powerball. So they give us all these things from Powerball. What do they say? Find the expected value of winning from a single lottery ticket if the jackpot is 30 million.
30 million.
So they say 30 million is our jackpot. So I guess we can fill that in since we're only doing one problem with this table. How much can you expect to win or lose each year if you buy 10 lottery tickets per week? Should you actually expect to win or lose this amount? Explain. What does it say? A single ticket is $1.
$1.
And we have all these odds, all these probabilities. This is the expected value. This is how you find it with insurance. It doesn't really change if we do Powerball lotteries. But if we buy 10 lottery tickets, I think that's probably the thing to start with. You are guaranteed to spend money. You're guaranteed to lose what? $10 on this thing is what you're spending on the lottery
10
tickets.
tickets, $1.
And the probability that you're going to spend $10 on 10 lottery tickets, it might seem silly because we're multiplying by 1, but there is a guaranteed possibility you're going to do that. All right, so do you think you could probably set up the rest of this thing without me telling you how to do it? We've done a few examples.
Come on, Professor, man.
Plus,
Don't do that, man.
yeah, I mean, I'm not just going to.
I mean, I understand how you may, this may be like a little, like, you know, above you. I mean, like you're above this, and you know, it's like, but I'm trying to learn this. I really need your help in, like, you know, really putting this together. So
I'm not trying to pretend like I'm above it or anything. I'm just trying to see if y'all can do stuff on your own. I'm just trying to give y'all a minute to think about it.
Goodbye.
So what's the first thing I'm going to put over here?
I
So
guess the million.
I would start maybe here is what I'm looking at. So what's the possibility? I'm spending $10. I could win what? This blurry ass number.
38.
It's 1 in 38 is the probability, is what it says over here. This says $4.
So
So would it be 4 times 138?
Yeah, exactly. And the next one, this also says $4. And what's the probability of that?
1 in 92.
Yep, 1 in 92. And the next thing, I could win
7, and that's 1 in 701. Really weird. 1 in 701. I could win $7 or another $7. I could win 1 in 580. So you got better odds with that one,
but apparently it's the same amount.
I could win what, $100. I could win that 1 in 14, 494.
So this, we're probably going to get pretty small decimals on a lot of these things, right? Okay.
So I should have 1, 2, 3, 4, 5, 6, 7, 8,
9, 10 different little things. I got 1, 2, 3, 4, 5, 6 of them. Continuing with this pattern, I could win $100, 1 in 14 out of 494 times. I could win $100, 1 out of 36, 525 times. I could win $50,000, 1 in 913129. So I'm doing the value by the probability, value by the probability, value by the probability. I could win $1 million. It is a lot of numbers that they're making us crunch here. 1 in 11, 688, 053. Or I could win 30 million. 1 in 292,000,000, 292, 201, 338. I ain't got much room left, but there it is. We do value by probability, value by probability, value by probability. So I'm going to have to add and subtract 10 different numbers here is what it looks like.
So, and then just to do the expected value of a single ticket, it would just be, instead of the -10 up there, it would be -1, right?
Find the exact value for a single lottery ticket if the jackpot is 30 million. Oh yeah, sorry, I like skipped to the second question right away, huh?
Well, I mean, it's just the same thing, just but with
Sorry, yeah.
negative.
Sorry, yeah, I thought they were saying 10 tickets and they're asking for 1 ticket and then they ask, well, if we buy 10 tickets. Yeah, I should be doing -1 because we're spending $1 for the ticket.
Right.
Yeah, that should be -1, you're right. And for the ticket, if we buy 1 ticket, that 1 ticket has 1 in 38 probability of winning $4, right? Has 1 in 92 of winning 4, 1 in 701 of winning $7. And so we're summing all these probabilities together. Yeah, if I did 10 tickets, that would change my probability. I wasn't thinking too much about that one, was I? 0.10526 or something. 4 divided by 92 is going to give me 0.04347. That's 3 things. 7 over 701 is going to give me 0.009985. Let's say 86. So I think I'm rounding them to like 5 or 6 decimal places. 7 over 580. 0.012069. One, 2, 3, 4, 5. 1, 2, 3, 4, 5. I think it's the 7 over 580 was the last one I did. Yes. Okay. 100 over 14494
.0068899. 6899.
Now I'm doing 100 over 365. 25. 002738. And before we even figure this thing out, should it be positive or negative that I'm expecting?
Negative.
Negative.
Should definitely be negative. 0.05477. 54757. 50K. Now I'm on the $1 million. So 1, 1, 2, 3, 4, 5, 6 divided by 11,688,053. $201. I can't read my own number. 338. Did I do that right? 30. 36. Yep. Okay. 1026. Okay, so I multiply my value times my probability. Now I got a smorgasbord of stuff to add. .757 plus 0.8556 plus 0.102669. Ooh. All right. Are y'all getting a number for this yet?
Getting there.
Yeah.
It is quite a few numbers to crunch. Okay. So if we crunch these numbers, it should be giving me like, what did I get? 58 cents. 57.6592. It should round to about 58 cents.
How's it still negative?
This negative, this is a -1. So all these fractions, they're not going to add up to more than 1.
Okay, cool. Thank you.
And in general, we should expect that, right? We should expect it to be negative because we're playing a lottery. We shouldn't expect to win a lottery, right? The lottery people are winning the lottery, is who's winning the lottery. And so what does this mean? If I buy a ticket, I can expect to what?
Lose 58 cents on it.
You're going to lose 58 cents per ticket that you buy in general. And now we're asking these questions. How much can you expect to win or lose each year if you buy 10 lottery tickets? Per week? What? Oh, God. Well, if you buy $10 in lottery tickets, how much are you going to lose?
580.
You'll lose 10 times this, which is 580. And then if you do that for, what, 52 weeks? You're gonna do that 52 times for a total of what, 301.60, I think is what I'm getting.
I have a question.
Sure.
So I added all of the numbers together, but I didn't get the negative 0.58.
These numbers?
Yes.
All right, so double check those numbers because I added them together and that's what I got.
Okay.
It should be like 0.57 and some change, but we're gonna round it up to 0.58.
Okay.
And I double checked that. That is what the book has, so it should be on. Should be correct. There are a lot of numbers here, right? If I'm being honest, this is a good homework question, but I'm probably not going to give you this many like outcomes, right? This many different events for an expected value problem. That's a lot of numbers. They're really ugly numbers. I'm probably going to make things a little prettier for you. But the concept itself, you should know the value and the probability, right? The value and the probability. We did this with the insurance earlier. This is very similar to the insurance problem. Now we're buying lottery tickets. Should you expect to win? You're going to lose that amount. Okay, I think we answered everything here, huh? It is a negative amount. We expect to lose it. All right, so we got a few more problems. This out of order. I got these backwards. Sorry. So that is that section. To me, I feel like, what is that, 7C? I feel like 7C is a little more important than probably 7D. 7D, I think they give you some really good numbers. They give you some really good numbers about reality, about mortality rates, about all these sorts of things. But I don't feel like they introduce any new sort of concept. They're just making you kind of crunch things that we've been doing in this section. Like 7A and 7B and 7C, they're all introducing something new and something pretty substantial, right? We're doing either theoretical probability or relative frequency. And what? That was part A. Part B, what would we do again in that section? I'm like blanking on that.
What did you say? Sorry.
In 7D, what was that again? I remember we did something. We introduced something big.
7D?
B.
7D?
B. Oh, it was
Combining probabilities. That's what we did. Yeah, we did the ands and ors. If things are or, are they like mutually exclusive, or is there some overlap? If they're an and, are we like drawing without replacement, and is it affecting the next probability that's happening, right? Or is it several distinct things happening with distinct probabilities? So 7A is like really important stuff, right? Finding probabilities. 7B is about combining them. 7C is about expected values in the law of large numbers. This one is like, let's look at a few statistics, right? It's like, it's there and it's good, and I think it's a good section to cover. But if I'm being honest, it's not as heavy as the first three. Or at least that's the way I kind of feel personally. Maybe you feel differently. Data in perspective uses data to help answer the following questions. US data of 2016 estimates. The car crash fatalities are around 40K. Yeah, y'all can read these numbers. 4.6 million for car crash injuries. 430, about how often, once every X minutes or X seconds on average, is a person killed in a car crash in the US? How often is a person injured in a car crash? Okay. So what do we want to do? We want to do what? Car crash fatalities per what year? Oh man, this is kind of like a review of those unit analysis things, right? If we got 40,
I
20.
had to go back in the book for that, or back in my notes for that. I was like, wait, what?
If we're doing it per year, ooh, 70 exercises. Okay. Then they want to know it per minute and per second. Is that what they're saying? Goal data, and this is, what are they saying? This is a different set of data? Is that what we got to do it for 2 of them? Is that what they're saying?
I think it just means decide.
How often is a person killed? What the heck are they doing? They're giving it for both of them. It looks like that one might be in 1995. It looks like this one might be, no, I don't know. They're giving me a number for 1995 and I don't see it. That's weird. Oh, never mind. I'm looking at the wrong problem. That might help. Sorry. Okay. So if we want to do this every X minutes or every X seconds, we got to convert a year to what? 365.25 days. I don't know if they're using the 0.25 or the 365. I guess we'll figure out pretty soon. And every
Yeah,
one day
365. Yeah, I think it's 1 year, 365.
is 24 hours. So we have done something like this. It's been a few nights and you probably slept on it. But we are going to end up doing some division here. So if I do 4,200 and I divide that by what? 365.25. Ooh, excuse me. Divide that by 24
365.
and I divide that by 60. Is this what they're getting?
I got 0.07643.
That's per minute.
Yeah, I got 0.0764.
Yep. What are they giving? They're giving, oh man. They're making, it's kind of annoying. They're making the fatality be 1 and the minute be a sort of thing. So I think we want to flip this is what we want to do so that we know how many minutes there is a fatality. I don't like this problem if I'm being honest too much. But if we flip this every 1 minute, we will have 0.07643 fatalities.
Hey, Professor,
Yes.
if you scoot your paper up, wouldn't it be 1 hour equals 60 minutes and not 60 seconds?
Oh, sorry. Yes, it should be in minutes. And I said in minutes. So yeah, it should still be the same number. Good call. Good call though. And so this is giving me fatalities per minute. If I want to flip it, I think that might be the easiest way to do. So every 13 minutes, I'm going to get 1 fatality. Okay.
Wait, how did you come to that?
If I divide 1 by 0.07643,
Oh, okay.
that's the easiest way to kind of do that one. We've got this far, and like that's pretty good.
So I got 13.083 as well. So do I round this? Or do I just leave it?
I don't.
Do I
Where you
round
at?
this to 13.1?
Yeah. So 13. It's about every 13 minutes, right? It's close enough to 13. So every about 13 minutes, we're going to get 1 fatality, is what this is telling me. or 13 minutes to every fatality. If they want to know seconds, we could go 13 minutes is every what? It's one fatality. 1 minute would be what, 60 seconds? So I believe there's going to be every 780 seconds, there is one fatality. Is another way of looking at that, right? Did I do that right? 1 minute, 60 seconds. Should be right. Why is it?
That's what I got.
About once every 13 minutes. Or they say about once every 7 seconds. Yeah, I don't know how they get into 7 seconds. It just seems wrong.
That'd be impossible if it's once every 7 seconds, because that means you'd have multiple deaths per minute, and we have one death every 13 minutes.
Yeah, I don't know what they're doing in the back of the book. That doesn't seem right. They're saying about once every 13 minutes or about once every 7 seconds. If you did once 7 seconds, that would be,
Yeah, that doesn't make any sense.
yeah, I don't know what they're doing. I wouldn't worry about it too much. My apartment's popping or something. I don't know. Okay, so we want to do this. What does it say? Expressed 1995 and 2015 fatality rates and deaths per 100 million vehicles miles traveled. So 1995, my traffic fatalities are 41,817, and the vehicle miles look like 2.4 trillion. So this was the kind of annoying thing that they do in the book, but we get 41,817. If we get 2.4 trillion, that's 4 billion. Okay, let me make sure enough zeros. I think I need one more zero, huh? This is thousands, millions, billions. We need more zeros. Here we go. Thousands, millions, billions, trillions. It should be 2,400,000,000,000. So if I look at 1995, it should look like this. If I look at 2015, let's set this up as well. Traffic fatalities are 35,092 out of 3.1, so 3,100,000,000. Okay. And so part A, if we wanted it over just, this is fatalities to miles, right? This many fatalities per this many miles. Okay, so this is the miles. And we want to compare it to what, 100 million miles? Is that what they're comparing it to? 100 million mile vehicles traveled.
Can I ask a question really quick?
Yes.
That's silly. Of course I can ask a question. So to convert it, I could also just divide like 41,817 by 2.4 times 10 to the fourth, right? I know in your lecture you said you could just like divide the zeros. That would be equivalent, correct? Because 2.4 trillion is 10 to the 12th.
2.4
And 100
trillion
million
times
is 10 to the 8th.
Yes, yes. And that's what I would do. So I wanted to make this to 100 million miles on bottom. So I know I'm going to multiply this number by 100 million to get to 2.4 trillion.
So that would be like, so saying what listening, I can't pronounce your name.
It's Lisa. I'm sorry. It was a mistake to do that.
Okay.
That's how it would
To
display.
get to from what she said, so do you put 2.4 arrow 12?
So what we're doing is dividing by what? 10 to the 8th is going to give me 100 million, right? Or I could do 100 million. So I'm going to want to divide this thing by 100 million, or I'm going to want to take out, essentially, I'm going to want to take out 8 of these zeros, right? 3, 6, 7, 8 is what I'm going to want to take out. And what this means is now I have what, 24 with 3 zeros? And this is 41,817 miles. No, shoot. Nope, not miles. Fatal, fatalities. Sorry. So that if I go back and I multiply, I think it's easier to think about it this other way, right? If I go 24,000 times 100 million, I will get back to 2.4 trillion. And so they're wanting you to divide these into 100 million miles. So we're dividing this thing by 100 million. And if we do that, now we're talking about in units of 100 million miles. It becomes a little bit easier to solve this, I think. 41,817 over what, 24,000? I'm getting like 1.74, somewhere in that ballpark. And this is fatalities per 100 million miles. If this gives us 41,817 over 24,000, I gotta do something similar to this one, right? So if I want to convert miles to 100 million miles, what I'm doing is I'm essentially dividing this thing by 100 million. So that's 3, 6, and 2 more zeros. So it should be 35 over 31, I believe, right? 012 over 31. Uh-oh, someone's not happy. Ain't my kid. Okay, so 35012, and we're past time if you need to go, but I will continue doing these. I should be getting 1.129, so somewhere around 1.13, somewhere around 1.13 fatalities per 100 million mile. And so if we want to compare them, in 95, it was what, 1.74. In 2015, it is 1.13. Does that make sense with like what you know about reality, hopefully? So from 95 to 2015, driving should have gotten safer, right? Is what it's saying basically. If we go from 1.74 to 1.13, we are dying less on the road a little bit. Okay.
Oh.
Okay. So that is deaths per the vehicle miles traveled. The other thing they want is what fatality rates and deaths per 100,000 population.
Oh, just kidding. I was looking ahead.
So this, we're pulling the same numbers, right?
For the fatalities. We're doing 41,817, but now we want to divide it by, instead of miles, by population. So does it make maybe hopefully it makes a little bit of sense why they're doing this. You want to compare probably your fatality rates to how many miles you drove on the road, right? The more miles you drive, the more likely you probably are to have an accident, something like that. 35092 divided by, this one should be the 321 population. And they want to do this per 100,000 population. So what it sounds like is that we're going to divide this by what, 100,000? We want to do that one per the 100,000. And so if I'm dividing by 100,000, where'd my red pen go? Here's a green pen. I think the easier way to think about these when you divide by tens or hundreds or thousands by powers of 10 is I'm taking away what, 5 zeros out of this thing? 3, 4, 5, I'm going to take away here. 3, 4, 5, I'm going to take away here.
So if I do 41,817 and I divide that by 263.0.
Hopefully I get the same thing they're getting in the back. 2630. 2630. Okay, it's coming up. So this should be 15.9, and we're doing fatalities to the population. And so these are fatalities per and you got to do the right units. So these would be fatalities per 100,000 people. So we get about 15.9 fatalities for every 100,000 people. So another way to think about this is like every 100,000 people on the road, there's going to be around 16 people dead, right? Who said we weren't going to think about wonderful, amazing things in this class today? But there you go. This one, I'm getting somewhere around 10.93. And these are fatalities per 100,000 people.
There was something kind of funny in the book that said the increase in a certain amount of fatalities was due mostly to an increase in people smoking marijuana while driving.
Yeah, I haven't seen anything substantial on that. Like I've seen things contradictory to that. Actually,
You see that?
Yeah,
happen.
no, I know that made me laugh. I was
Just
like,
putting some stuff
okay.
out there, Lisa. What are you doing over there?
there's a little grain of truth to that.
Some list out there. Hey,
There was a slight increase.
started some stuff this morning. Huh?
There was a slight increase when it first happened, and this goes back to like the statistics things, right? If you cherry pick certain numbers, you can get like almost any sort of narrative going if you cherry pick.
No, that's why I thought it was funny because it was so ridiculous. It reminded me of that one like commercial where those two stoners were driving through the drive-through, and then they like hit a kid, and they're like, "That's what happens when you smoke and drive." And I was just like, "What kid is riding their bike at 3 a.m. anyways?"
Yeah, really. At 3 in the morning.
So
Sorry, that was an aside. I just,
No, that was a good one.
has some like really pointed statistics where I was just like, this is definitely aimed towards college kids.
Oh man.
Yeah,
That's
I mean,
funny.
okay.
Sorry.
1995 and 2015. Yeah, I can't say that the data that I've seen really supports that. Like, there's really hard to conclude one way or another on like how much it does affect your driving.
Well, and then how many studies have been done in the past 30 years where they actually even took, you know, somebody under the influence of marijuana into effect?
That and you have to rely on people wanting to be honest about being under the
Exactly.
influence of marijuana. And when you arrest people for it, people aren't, you know, always very honest with how much they're doing. So fatalities and deaths per 100,000. Oh man. So we're doing like kind of the same thing over and over here. We're taking the same number, 817 for 1817. Ooh, sorry, 35. Sorry, wrong number, 35092. We're doing fatalities. Now we're changing the denominator. So each time we're changing the denominator to whatever the heck they tell us. Per is that word that means division. We've gone over this before when we did unit analysis. So per 100,000 licensed drivers. So we do it per population is a good way to get at how many people out of your total population are driving. Per licensed drivers would be a good way to get at how many people actually driving are getting killed, right? 100,000 drivers. Now where we're at. 218 is this one. 218-000-000. And they want to do it per 100,000. So the easiest way again is just to divide this by 100,000 to see how many 100,000s are in here. And if we're dividing by 100,000, again, what we're doing is we're just shifting the decimal place. We're shifting it 5 zeros is what I needed to count for. I count the zeros. There are 5 of them. I want to take out 5 of those zeros. 441,817. Divide by 177.0. This is giving me 23.6 in this one. Let's say 625, just for grins. And this is like fatalities per 100,000 licensed drivers. $35,092, and we're going to divide that by what? 2180. That 2015 number should be giving me 16.097, somewhere in that ballpark. It is in the same thing, fatalities per 100,000 drivers. And the other thing that's really kind of hard with like causal sort of links like that is that you have things called confounding factors. There's like other factors that could be at play with making accidents go up or down, right? Besides just the consumption of whether they consume cannabis or not. Like Colorado is one of the places that legalized, and it's like that is nothing but about a bunch of mountains and snow. Like you're probably gonna have more traffic wrecks. And if you get tourists, right, in Colorado, they don't know how to drive on Colorado roads. These things can all like influence things, right?
Yeah, and more people are going there because we just legalized. So
yeah. So there are a lot of factors that can sort of play into these things, and you know, the whole purpose of an experiment is that you isolate factors, right? You try to isolate factors and have only one variable and have multiple like sort of controls to make sure it is the variable that is influencing things. The table shows the number of accidents, fatality hours flown in miles for U.S. airlines with scheduled service in selected years. Whew, here we go. There's a table. Compute the accident rate per million hours flown in 2000 and 2015. By this measure, has travel on U.S. airlines become safer? So it looks like we're looking at the first and the last. We're doing accidents per million hours flown. Oh man, this is a nice way. We get 49 accidents. Accidentally get accident rate. 7 million hours. What do I have to do to convert this? And maybe it's a silly question. This A, yeah, there's two parts. Is that, do I have to convert it? This one, they were a little nice. They said accidents per million hours, I think, right?
Yeah. So we have to do the hours.
So this is it. This one, you don't have to convert. This is 2000. 2015, it is already in the units they say it is. So they're a little nicer with this one, 27 accidents per 17.4 million hours flown. And they give miles and billions. I bet we're going to compute miles next, huh? Compute the accident rate per billion miles. So the next one is computing it per billion miles. So it is going to be very similar, except we divide by the billion miles. So I hadn't even crunched these numbers yet, but I know I'm going to do 47 accidents. I'm going to divide that by the number of billion miles flown, which is 7.1 billion miles. And then the other one is 27 over, what, 7.6? That's it.
It's 2.93.
I'm just setting them up. I hadn't even solved them yet.
Oh,
So one says accidents per mile, one says accidents per, accidents per hour, and then accidents per mile is what we're doing. 49 divided by what, 16.7? Give me somewhere 2.93 is what you said?
yeah, that's what I got, 2.93.
And this is accidents per million miles. Is the units on this thing. 27 over 17.4.
1.5. Do you round this off?
1.55 is pretty good.
Okay.
So what are we going to say about travel between what, 2000 and 2015? Did it become safer? If we do accidents per million miles,
Yeah.
it's about half of it, right? About half the accident rate. So that's pretty good. If we look at this one, accidents per what, billion miles. Now we're going to go per mile that was traveled. 49 divided by what, 7.1? No, wrong number. 49 divided by 7.1 should give me around what, about 6.9 probably. 27 over 7.6 should give me about 3.55. And this is accidents per billion miles. I said miles on this one. Whew. Should not be at miles. This was hours. Sorry. This was hours. Sorry, got the wrong thing. I like had it right on here and then I was looking at the wrong spot. So when we compare the amount of accidents to the amount of time, this is about twice as safe, right? If we compare the accidents per billion miles, still about half as safe, right? Which should make a little bit of sense if we look at the table. I think the fatalities probably go down, or the accidents actually go, fatalities go down way more. The accidents are about half. 27 is about half of 49. The miles flown and the, what else? The hours flown aren't changing all that much, right? but these are about half. So if your accident's half, you would expect that number to half if your denominator is not changing all that much. It says my internet connection is unstable, so I might start cutting in and out. Or just make those sounds and make it sound like I'm cutting in and out. Who knows? Over. This is 19. If you lived in typical US city of about 500K, how many people would you expect to die of a stroke in a year? So this is going back to table 7.5, which I didn't, but it is in your notes. They are using this vital statistics. So oh, they're doing the deaths per population. What was the US was they were using 325 million, I think, right? It's about 328 now. This they want to know for stroke. So REO Speedwagon it. What is this? 133, 100.
Okay, so
I'm doing 133, 100. And I'm doing that over the 325 million people that are in the US. This is stroke per people, right?
so we use the 325 instead of the 500,000, right?
325 instead of the 500,000 is what we're going to have to figure out, right?
Okay.
There are a few ways to do this. You can find how many strokes per people, and then you can multiply it by the 50K, 500K. That is absolutely one way you can do it. You can divide these and multiply it. What we're doing is we're like trying to figure out how many strokes.
Yeah, so you say the 133 divided by 500 would give me the same answer?
No, you'd have to do the 133 divided by the 325.
And
then you'd have to multiply it by this.
Okay.
Because this will give you strokes per people, and if we're doing 500,000 people,
Okay, I got it. Yeah.
one way is to think that they are going to be equivalent fractions, right?
Okay.
Another way is we can do 133, 100, divide by 325, 123, 123. This gives me like 0.3 zeros and a 4095. If I did this and then multiplied it by what, 500K, this is another way to find it. If we did equivalent fractions and did the butterfly thing and I put this as my X, I would be getting the same number, right?
Okay. All right. That's what I'm about to do right now. I got 0.00409. Do you add the 5? Do you add the 5 with this? How many numbers you say? 3? Oh, 4. Oh, I see. Never mind. Never mind. I see it.
This is stroke, right, per person. This is the 500,000 people.
Yeah.
So this should give you the total amount of what strokes? People with strokes. So about 205 people is what we'd probably expect, right? About 205 strokes. I'm gonna have this song stuck in my head all day today now. Dang it. Okay. So we could cross multiply it. That's the other way. Either way you do it, it's the same approach basically. Whether we divide this and then multiply it by the 500K, that's how we would solve for X anyway if we were going to solve for X. Or you could do butterflies. Either way, you should be getting somewhere around what, 205? Okay, 1921. And we got 2 more. Okay. Estimate the death rate for 60 to 65-year-olds using figure 7.14, assuming there were about 14.2 million 60 to 65-year-olds. How many people in this bracket could be expected to die in a year?
So
Death rate by age. I think is the one we want to look at. There is a life expectancy by age that we looked at in our notes. 60 to 65. Looks like somewhere.
what they're saying, 60 to 65. It's like it's going to be about 10 years. Or a death rate per 1,000.
10 per 1,000 is what it looks like.
Yes. 60 to 65. 1, 2.
So I'm going here at 60. I look along here. It's going right over the 10. It's like right below and right over, I think.
Yeah.
About 10 deaths per 1,000 people. Is that what it says? Let me make sure I count my zeros. Yeah, 1,000 people. So that is the number we're grabbing from the table. And we want to estimate the death rate for 60 to 65-year-olds. Are they wanting just the decimal? I'm not really sure. 1,000. If we crunch this per person, 10 over 1,000 will give us like what, 0.01 deaths per person?
Yep, that's what I got.
And what is this? This is 19, this is 21. They're saying, they're assuming 11, 10 is probably close enough.
There were 14.2.
How many people in this bracket could be expected to die?
142,000.
We're doing 142. So we're doing 0.01 deaths per person. So if you do unit
14.2
analysis,
million times.
yeah, if you do a unit analysis, this thing should be matching up, right? Deaths for every one person. And if we multiply by how many was it? 142 million? 14.2 million. So 14,200,000 and 3 more zeros. And this is people, right?
Mhm.
If we want, we could like put it over 1, but people and people should be simplifying out. And we should be getting deaths if we multiply these things together. 14,200, 1, 2, 3 times 10 times 0.01. They say 142. Yeah, in the book they said 156 because they did 11%. Ooh, wow.
Why did they change it to 11 or 1?
They're guesstimating from the graph is what they're doing.
Oh, Lord.
We guesstimated 10 because I would guesstimate an even number if I had to guesstimate something.
Okay, I got it.
Either way, as long as you're showing your work, I'm not going to count off for like reading a graph 1 cent off, right? 142 deaths. Okay. And we got 2 more problems.
Once you move that up there, 1, 2.
Birth rates, the highest and lowest birth rates in the U.S. in 2015 were Utah and New Hampshire. All right. Utah reported 51K births, population of 3.3 million, and New Hampshire reported 12K births with population of 1.3. Uses data to answer the following questions. On average, how many people were born each day of the year in Utah?
Okay. So I'm going to take the 51, 154, and divide it by what number?
If this is manual,
365.
yeah, I got to divide this by 365.
Right. And I think on average, how many people were born each day in New Hampshire?
So this is A. B is going to be the other number divided by 365. So these are the same approach. They're basically the same problem, just different state. Births per day divided by 365. If you really want to be accurate, you could probably do 365.25, but I'm not. I'm getting around 140.15 here. 12,302 divided by 365. I'm getting around 33.70. And here our units are bursts per day. So in the book is probably going to round it to the nearest person. And typically you probably should do that. So if we're going to do that, this is going to be what? 140 bursts per day. If we're going to round this, I think it's going to round up to what, 34?
Yeah, just 34. It's 33.7, but if you wanted to, you could.
Yeah, we don't want to quarter a person up. We're not.
Okay.
What's that? What is that? Is it King? Oh, I can't remember. It's not Midas.
Solomon.
Solomon, that's it. And it split the baby in half. Midas was the gold touch. That's right. What was the birth rate of Utah in births per 100,000 people? So Utah has a 51,154 births for every 3 million. And we want it in, what did I say, 100,000? We want it per 100,000 person. So that is what, 3, 4, 5 zeros I need to mark out. It looks like 3, 4, 5 zeros I need to mark out. So 51,154 births divided by 30. That seems high. No, that's right. Okay. 1705 births per, that's right. We're going per 100,000. It would be higher. I don't know. My brain is like, my brain's done too much math for the day, I think.
Oh my God. Stop it. Stop it.
And
Let me see this.
D is going to be very similar. We're going to do births per 100,000 people. 12,302. We're going to divide this by 1.3 million, which is 1300000. I want to divide this by 100,000, which is going to give me 5 decimal spots, right? So I'm looking 3, 4, 5. It looks like I'm doing 12,302 and dividing that by 13. I'm going to get around 946. And the last problem. They just wanted us to do A on this one. So they said, make a table showing the percentage of Americans over age 65 between 1950 and 2015. $19.50, $19.60, $70, $2,000, $20,000. And 2015. So if we want the percentage of people over 65, there's this many people over 65. Man, did they really make us do this? How do I figure this out? if I want to know the percentage,
So you would add, wouldn't you add all the millions, the population millions together, and then divide them by 1, 2, 3, 5, 6, 7, 8?
they're wanting to go year by year. So I'm looking here. If there are 12.7 million people over 65, and there's a total of 151 million people, what am I doing with these two numbers to find the percentage of people that are over 65?
Dividing them.
Divided.
Dividing them. What percentage is this of this is what I'm saying. 12.7 divided by 151, 0.084, somewhere around there. So you could say it's about what, 0.4%, I think.
Okay, so I'm gonna divide all of those. All right, so you don't have to
Yeah.
divide all of those because I think I can get this one.
But it's not too difficult, right? We're just dividing two numbers here. So 8.4, I'm just gonna hurry up and do this. This is 9.6. Just take those two numbers and divide them. And convert it to a percentage. And this is the last problem that we're doing here.
Yep.
It's the last one that's assigned. So there you go.
Yeah, I think I can do this one.
Yeah, this is a fair
This
question.
one's pretty easy.
Yeah.
That other one was kind of tricky, but this one is pretty laid back. I can go all the way to E on this one. I'm pretty cool on this one, Chris. I'm gone. All right, I'll see you next week.
All right, see y'all. We will be
Thank
doing
you.
the quiz next week, so I will get that up next.
Got it.
Okay.
Thanks. Have a good one.
All right, y'all take care. Thanks for
Yeah.
sticking around.
Yeah.
And I stopped.